So here we have the alum crystals and the update on them. They have grown a nice sheet layer on the bottom of the vial, and along the sides there are some growth that did happen but did not fully form because the solution had evaporated. And one reason actually why there isn't one big condensed crystal as expected is because early on the transportation from the lab to my room, there could have been some shaking and breaking up of the bonds. And to make the previous videos, I picked them up and transported them, which could have broken some of the bonds to help make the one big crystal. And also, it did like tip and spill a little bit, but that still doesn't seem to affect the results. It's pretty pure looking crystals, just not in the size and quantity that is expected. But to make a big crystal, all that I believe you need to do, as I mentioned in the last video, is to hold a string up to the vial and suspend a small made crystal in that vial, and then as the solution begins to evaporate and the concentration within it grows, the crystal will grow to just form one dense crystal in the middle of the vial. And so, speaking of structure of crystals, there's a little thing called despacing. And so for the despacing, it's a pretty complicated and conceptual topic. It's mostly the space in between the planes of the crystals and how they end up forming. So to calculate D, there is a Bragg's law equation to help with that. So it is 2 times the D space times sine of theta equals the molar ratio times the wavelength. And so for this, we are just going to assume that N equals 1, and then the wavelength that is given is 0.1518. And so in this chart, the peak is at, I just estimated at 20 degrees. And so since that chart is in 2 theta, it does need to be converted to just theta so that the equation can fit. And so just to explain a little bit more about D-spacing, and it is the planes as here. It is the space between them, and these little dash marks are just the IMFs, and this is just a crystalline structure. And if the spacing is smaller, then it is a more dense structure, a more dense crystal, and if it's bigger, it's less dense. And the density, the packing, and the D value determines the properties of them. And so to determine the D value of this crystal, it's more of a plug and chug. You just plug in the values as mentioned before, and what you get out is 0.44 nanometers as the D, which is the space, as I said, between the planes of the crystal to help make the structure. And so this also, D is significant because it makes the unique unit cell, and so Bragg's law is key to learning everything to know about a certain crystal. And it is great to realize and understand more conceptually what crystals and intermolecular forces do to the properties physically and chemically of a structure.